Hi everyone. So in this video, we'll be continuing the solutions to IOQM mock, and in this particular video, we'll be discussing first five markers. That is problem numbers 21 to 25. Since these are like slightly harder, like at least I hope that they're slightly harder. So I do not want to like do all that in one video, so I'll divide it into two parts. So let's quickly begin. Let's see problem 21 first. I think this problem was on like a hard side. So ABC is a triangle, right angle triangle at A with AB equals to AC. M and N are points on BC such that one sec. BM square plus NC squared equals to MN squared. And we have to find this angle. So the first instant when you see such thing, like square of one thing plus square of another thing is equals to square of third thing, is like there is some sort of Pythagoras involved. But obviously there is no direct triangle here. So how do you use Pythagoras theorem? Okay, moreover, another thing, like AB is equals to AC, and the problem is like symmetric about the angle bisector of A here. Like everything is just symmetric. So you would expect that, oh, M and N is like something like 45, which is a symmetric to 90 thing. But that is a very rough way to guess. Uh, okay, I'll reveal that like 45-degree is the actual answer. And in contrast, like I would say that you can guess this way, but obviously it can be like something like 30 as well. You never know. So let's just see how to solve the problem. Um, okay, since this is like symmetric and you want to involve some points, so like you want to construct a triangle where you can use this thing, right? So what we can do is we can okay, like Mn should be the hypotenuse, and Mn and are the other two vertices as well in here, right? So we take a circle with center M and radius MB, like a circle like this. And we take a circle with center N and radius C, like circle like this. And see at what point they intersect. Let's call that point as X. Now, MX equals to MB and NX equals to NC. So this implies uh, B, sorry, MX square plus NX square equals to MN square. So this angle here is 90 degrees, right? So in this case, like, see, like this is like a decently good diagram. And here you can like make some guesses, like claims. So like AM sort of looks like bisector of angle BAX. And moreover, like this side is oh sorry, not this side. Like these two sides are equal. This side is common, and this side is equal to this side. So like there is some sort of hope that like these two triangles are congruent somehow, like ABM and AXN. So let's try to work on that intuition. Also, let's see what happens when this is the angle bisector, basically. Like if this is the angle bisector here, by symmetry, you can say that this is the angle bisector here as well, right? And then everything just works out. The angle is just 45 degrees. So this looks like that it can be true. So let's try to prove that it is true, in fact. Uh, A, B, C. Okay, not a good diagram. A, B, C, M, and N. So now what we do is we define X to be the reflection of B over M. This is X. So this way, BM equals to MX and AB equals to AX. Notice that AB equals to AX equals to AC, right? And we got that uh, BM equals to MX, right? Um, okay, so now we have to prove that to prove AN is angle bisector. Like this should be true by symmetry. I mean, like intuitively at least. So let's try to formally prove this. Define a point N dash. So like define N dash on BC such that AN dash bisects angle XAC. Basically, this is called phantom points. So let's say that this point here is N dash. Then, since this is the angle bisector, right? Uh, we have AX equals to AC already. The two angles are bisected, and uh, AN dash is common. So triangle AN dash C is congruent to triangle AN dash X, which means XN dash equals to N dash C. And we already know BX equals to BM equals to MX. So you get MX square plus XN dash square equals to MXN dash. Wait, sorry. What am I writing? No, no. Yeah. We don't have that. Okay, yeah. So let's see what angle MXN dash is first. Like, this should be 90 degrees because n is equal to n dash. We know that. So let's just see what it is. This is equal to angle MXA plus angle AXN dash. Angle MXA is angle MBA because these two triangles are congruent, plus angle AXN dash equals to angle ACN dash, similarly like by congruency. And these two angles sum up to 90 degrees. So we got that this angle is 90. So now by Pythagoras, mx square plus n dash x square equals to m n dash. Mx square is equals to bm square and n dash x square equals to n dash c square. So bm square plus cn dash square equals to mn dash square. And like we know that bm square plus cn square equals to mn square. So this implies n should be equals to n dash. So everything which we guessed here is true. So now angle MAN is equals to angle BAC by 2, which is like you can write angle MAN equals to angle MAX. Let's take a different one. MAN equals to angle MAX plus NAX. Angle MAX is like this angle by 2, and this angle is this angle by 2. So overall, this is 90 by 2, which is 45 degrees. So the answer to 21st problem is 45. Let's move on to problem number 22. So in such a problem, like, okay, you just have to find all n for which there do not exist a solution to this equation. So in such a problem, you'd try like some base case for n, like try n equals to 1, 2, 3, 4, 5, 6, 7. And eventually you'll see that this does not work, this does not work, all these work. So this makes you guess that every n large, like all large enough n would work. Something like all n greater than equals to 3 work. That seems to be the case here. So let's see how we can formally prove this. So basically 2 to the power n equals to 7x square plus y square. We want to like decompose in some sense such that this is like 7 plus 1 in some way. So basically like, it will be clear when I write it. So we can write this as 8 times 2 to the power n minus 3, which is 7 times 2 to the power n minus 3 plus 2 to the power n minus 3. Now, if n is odd, let's say if n is 2k plus 1, this implies 2 to the power n equals to 7 times 2 to the power 2 times k minus 2k minus 2k minus 1 plus 2 to the power 2 times k minus 1, which is equals to 7 times 2 to the power k minus 1 squared plus 2 times, sorry, 2 to the power k minus 1 squared, right? So you can take this as your x and this as your y. So a solution clearly exists. The only thing here is n minus 3 should be greater than equals to 0. So this implies n is greater than equals to 3. But this was for odd n. Let's see what happens for even n. Uh, n equals to 2k. So 2 to the power 2k equals to, see, like this 8 idea will not work anymore because this worked for like odd n. So let's try to take something higher than that. Let's say 16 times 2 to the power n minus 4, which will be 2k minus 4. And then I can write this as 7 times 2 to the power k minus 2 whole squared plus 9 times 2 to the power k minus 2 whole squared. But I can write this as 7 times 2 to the power k minus 2 whole squared plus I can take this inside 3 times 2 to the power k minus 2 whole squared. And now this can be my x and this can be my y. So this is a possible solution. But for this case, 2k minus 4 must be greater than equals to 0, which implies k must be greater than equals to 2, which implies n must be greater than equals to 4. So for all n greater than equals to 3, I showed you that there exists x and y, right? Now, so like there's a solution for all this. Now 1 and 2 is left, right? So for n equals to 1, 2 equals to 7x square plus y square. Obviously, you can check no solution exists. And for n equals to 2, 4 equals to 7x square plus y square. Uh, there should be positive integers. So like x, like this is at least 8. And same argument follows here. So no solution. So for 1 and 2, there is no solution. So that is what we wanted, right? So the number of such numbers is 2. So the answer to this problem is 2. Let's move on to problem number 23. If you have seen complex numbers before and like complex representation, this is like a very standard complex number problem. So I plus root 3 by 2. Like I can write this number as um okay, like you should know this thing. Like this is called Euler's formula, I think. E to the power I of theta is cosine theta plus I times sine theta. Like you read this when you study complex numbers. Like you can look up on Wikipedia to see a proof of this if you want. But this is a very famous formula for complex number and like helps to deal with complex numbers nicely. So like this number root 3 by 2 plus I by 2 can be written as cosine of 30, yeah, 30 plus I sine 30 degrees, which is e to the power I times 30 degrees. So now raising it to the power 2023 becomes e to the power I times 2023 times 30 degrees. Correct? And now, like, you can clearly see that cosine and sine are periodic functions with period 2 pi. So e to the power I theta is like periodic function modulo 2 pi. So I can like take out some 360k. Like this thing will be same. So let's find 2023 times 30 degrees modulo 360. And okay, this is basically bunch of computation, but I'll just tell you what the final value is. Is two so the value is 210 degrees modulo 360. So this term is e to the power I times 210 degrees, which is cosine of 210 is cosine minus cosine 30 minus root 3 by 2 also in tan minus 1 by 2 iota. And the other thing, so this is basically cosine of let's see, cosine minus 60 I think cosine of 120 degrees plus sine of 120 degrees times I. Okay, what is sine of 120 degrees? This is same as sine 60, right? Okay, not 120 then, 150 it should be. Yeah, so sine 50, 150 is sine 30, which is 1 by 2 iota and minus root 3 by 2. So cosine 150 is minus cosine 30. Yeah. So this is e to the power I times 150. And then you raise to the power 2023, it becomes times 2023. And you just take this number modulo 360. Uh, Modulo 360. Let me calculate the value. So 2023 times 150. And you have to take modulo 360, which is okay. This is slightly hard to calculate. Uh, 720 plus 720. Yeah, so this is minus 30, which is 330. So this thing is 330 modulo 360. So this thing here is e to the power I times 330 degrees, which is cosine of 330 degrees is cosine minus 30, which is cosine 30. Cosine 30 is root 3 by 2. Sine 330 is sine minus 30, which is minus sine 30 minus 1 by 2 iota. So if you add the two terms, you'll get minus iota. And you have to find minus 25 x squared, like this is x. So minus 25 minus iota squared, which is minus 25 times iota squared, which is minus 25 times minus 1. So the answer is 25. So the answer to this problem is 25. Like, I think this was a very standard problem if you know complex numbers. Like, a lot of people said that why is this even a 5 marker? Because there are any complex numbers. But I think if you do not know complex numbers, this can be slightly complicated for you. Okay. So let's move on to problem number 24. So we have 4p of x squared equals to 4p of x whole squared plus 4p of x minus 1. I can write this as 2p of x whole squared plus 2 times 2p of x plus 1 minus 1. And okay, rather I can write it like this. P of x, like we just divide by 4 on both sides. This just makes it like easier to deal with coefficients. And this thing becomes P of x plus half whole squared. So P of squared plus P of x plus 1 by 4 minus half. So this implies P of x squared plus half equals to P of x plus half whole squared. So this is a very standard thing here. Define Q of x as P of x plus half. And this will give you Q of x squared equals to Q of x squared whole squared. And now if you take Q of x to the equals to x to the power k, then Q of x squared is x to the power 2k, which is x to the power k whole squared, which is Q of x whole squared. So basically all functions Q of x equals to x to the power k work, which means P of x must be x to the power k minus half. We have to find the sum of all values of P to 2023 over 100. Now the issue here is, if you take k as like, let's say, any value, like P of 2023 is 2023 to the power k minus half. And k ranges from uh 1 to infinity, right? So like actually you can take, okay, it should be an integer because polynomials have integer degrees. But anyway, so the point is like this sum will tend to infinity. So this is basically a bonus question. Like the sum is not defined. I did not like see all solution. I like miss this. So I thought like the value is a finite number and hence the issue. So yeah, this is a bonus problem. Okay, let's move on to the last problem of this video, problem 25. So ABC is a right isosceles triangle with right angle at A. A, B, array, C. A and F be points on AB and AC such that angle ECB is 30 degrees and angle FBC is 15 degrees. Line C and BF intersect at P and AP intersects at D. So we have to find angle FDC. So let's just try to angle chase a bit. So like this is 30, 15. So this angle would be 135 degrees, which is 90 plus 90 by 2, which is which is angle BAC by 2 plus 90 degrees. Which means if we consider in center I somewhere here, then this will be a circle. So like this is basically a nice circle, right? And moreover, the center of this circle is intersection of the external no, not external angle bisector, but okay, let's try to find the center of the circle. Let's call that point X. Then angle BXC would be twice of angle VAC. Huh. Okay. So in center is slightly drawn at the wrong position. I want a better diagram. Let's draw in center somewhere here. Yeah. So okay, like this point by fact 5, which is called in center X center lemma, is basically like lies on this circle and is intersection of AI with this circle. Now AI is just angle bisector. Like this is 45 degrees and this is 45 degrees. So by angles, you can show that ABXC should be a square basically. So that is how X is defined. Okay, let's just move the circle for now. So this is how we get X. And what do we have? Like X is the center, right? So XB equals to XC equals to XB. So now we got a new point. Let's try to angle chase more. Hmm. So this angle is 45 degrees. Let's see any other angle. This is 45 degrees. Okay, this whole angle is 60 degrees, right? So this angle is also 60 degrees. And this angle is also 60 degrees. So this is equilateral. So XB equals to BP equals to XP. And we know that XB equals to BA because ABXC is a square. So BA equals to BP, which means okay, wait, which angle do we have to find? FDC, right? Okay, B equals to BP, and you know that this angle is 30 degrees. Like this angle is 15 and angle B is 45, right? So this angle here would be 75 degrees, and so will this angle, which means that this angle will be 15 degrees, right? And this angle is 15, this angle is also 15, which means FABD cyclic. Now we have to find angle FDC, right? So angle FDC is just angle BAF, which is 90 degrees. So the answer to this problem is 90. So 25 is 90. So like the main point of this problem is you just chase angles, like as many angles as you get, and you try to make observation. Like this observation here was important. So like once you make this observation, you identify the circle, think about what you can do with the circle. You can introduce its center, and the center comes out to be nice. Okay, now define the center and find more angles. In contest, you'll find way more angles than I found. Like I knew the solution, so I just marked the relevant angles. But you can like find like let's say this angle as well if you want. I don't know if it's findable, but like you might want to try that or try to find this angle or this angle, stuff like that. Okay. So yep, that was it for this video. And in the next we will discuss the last 5 questions. I'll stop recording.